Hello, everybody. This is going to be Universal Gravitational Lecture number 3. Lecture number 3. So the first day we talked about the force of gravity being big G m1 m2 over r squared. And we also talked about the acceleration due to gravity. Okay, and then on lecture number 2, we talked about Kepler's laws. All right, so today we're going to talk about potential energy. So potential energy, at least gravitational potential energy. Remember, we're going to use this capital U sub G, gravitational potential energy, is stored energy as a result of its position in a gravitational field. Now, up until this point, we used MGH. We used MGH to define that. Okay, and we will kind of go back to that here in a minute. But what is a gravitational field? What is a gravitational field? All right, so we're going to kind of shift directions here. And you guys are probably more familiar is if you had a bar magnet, and I'm sure you guys have seen this. If you take a bunch of iron filings and you put it in the presence of a bar magnet, which is a north and a south pole, then you're going to end up with these magnetic field lines that are going to go out like so. And you might recognize this and you get something like that, right? If you have not seen that, if you just Google magnetic field of a bar magnet, okay, you'll probably see something will come up, either that diagram, and you can, I'm sure, look up a video that will show you that as far as iron filings go. All right. Now, you also know that when you get farther, if you've got two magnets together, right? So if you are north and north pole, they're going to repel each other. So as the closer you get, the more repulsive they become. It makes it harder to push together. Now, if you flip it over and you have north and south, right? It's an interesting thing. How close can you get them before they snap together? So remember, that magnetic force is going to be governed by the inverse square law. So as you are bringing them closer and closer, right, you're resisting them getting closer and closer. Your force is going there. But because it's a result of the square of the distance, or 1 over the square of the distance, as you increase that force, okay, it's going up and up and up and up, and you don't have time to resist that as it increases. Right now, you clearly have the strength to keep them apart, right? Because if you take two magnets, you can pull them apart. You have the strength. You just don't have the reaction time as they get closer. All right, now we're going to have the same concept. On the Earth here. So if this is the Earth, okay, we're going to have a gravitational field, and that gravitational field is G. Okay, it is the acceleration. It is the acceleration due to gravity. So that gravitational field at the surface of the Earth is going to equal to 9.8. It's going to equal to 9.8. If we come over here, okay, it's going to be 9.8. And if we go here, it's going to be 9.8, 9.8, 9.8. Okay, so in fact, anywhere on the surface of the Earth, it's going to be 9.8. Once more, you guys, because gravity is only attractive, we're not getting those weird sort of shapes there. So the gravitational field around a sphere is always just going to be pointing towards the center. It's always going to be pointing towards the center. But what if we end up going one more Earth's radius, right? So now we have a total of 2 Earth's radius. You guys, we're still going to have a gravitational field. We're going to have a gravitational field. But at this distance, okay, at twice the distance, we're going to have a value of 2.45 versus 9.8. Because inverse square law, we're going to have 1 over 2 squared. So it's 1/4. It's 1/4 that value. So we could draw vectors here of a certain length. And if we were to go twice the distance, that this vector would be 1/4 the size. Okay. And if we went out another Earth's radius, okay, now we're going to have something that is 1/9, which is going to be about 1.1, right? So the gravitational field lines are all going to point towards the center. But as you go farther and farther away, that value, the strength of that gravitational field is going to decrease, right? So presumably somewhere near the surface here is going to be 9.7 and 9.6 and 9.5, okay? Now, what perhaps is counterintuitive, it's not linear, okay? It is going to be exponential, and it's just to the second order, right? It's going to be kind of parabolic or quadratic. Again, because of the inverse square law. All right. So now, if we go back here to our gravitational potential energy, we've always used MGH. And you may not remember, but I said we can only use that when we're near the surface of the Earth. Because near the surface of the Earth, it's going to have a value of 9.8. Even if we can get as far away on the surface of the Earth as we can, let's say on top of Mount Everest, I believe, without having done the calculation, I believe that the acceleration due to gravity at that location is something like 9.77, 9.78. And that would round down to 9.8. So it's still even close, even on the surface of Mount Everest, right? It's going to be as far as you can get away. You're going to have a rounded value of 9.8. But as we get farther and farther away from the surface, it's going to essentially go down to zero, or it's going to approach that sort of zero. So we need a formula to determine what is the gravitational potential energy that takes into account that changing value of that gravitational field. And that's what we're about to do. Okay, now this is kind of weird, so you can kind of stop and move along here. So we're going to review a few concepts here. Okay. Now, you guys, we know that mechanical energy is equal to kinetic energy plus potential energy. Okay. And we know that work is force times distance. You may also remember that work is equal to the change in kinetic energy, and it's equal to the negative change in potential energy. And if we just think about a pendulum, okay, or a car on a roller coaster, right? When we are at the highest point, let's say in a pendulum, we're at its highest point. As it goes back and forth, it's going to momentarily stop here at its highest point, which means the kinetic energy is greatest, okay? Its gravitational energy, being at the highest point, would be the greatest. Now, as we let go, as the mass drops, its kinetic energy is going up. At the same time, its potential energy is going down, right? So the change in kinetic is equal to the negative change in potential. All right. So really, because this distance or this force. Now, normally on the surface of the Earth, we would say that that's mg, and this d would be h, right? So that's force times distance. Okay, so essentially what we're going to have here, work would be equal to the negative change in potential energy, which would be the negative integral of f dr, okay? So the negative in there because we're talking about working against potential energy. Well, the force of gravity is equal to big G, mass of the Earth, times any other mass, let's just say like 1 kilogram, divided by r squared. Okay, so now we're going to put in this force right here. So now we're going to take the negative integral of big G, mass of the Earth, and we can just call that for now, we can just call that m1, m2 over r squared. And we're going to go from r initial to r final, okay? And then we're going to have dr. This right there, those are all constants, so they can come out in front of the integral. So we're going to have negative big G m1 m2 times the integral of dr over r squared. We could also think of this as r to the negative 2 dr, okay? From r initial to r final. Again, we're going to have this big G m1 m2 in front of that. Well, this, if we do the integral, that's going to be 1 over r negative, right? And we're going to evaluate that from r initial to r final, okay? And so as we come back here, we can say that the change in potential energy is going to be this negative times this negative, which is going to turn into positive. So we're going to have G m1 m2 times 1 over r final minus 1 over r initial. Okay, so this right here is going to be our equation for the change in potential energy. All right, now, you guys, this next concept is a little bit weird, or at least it was weird for me. Okay, so we're going to just think about this for a moment. I'm going to say that my hand, is 0. I'm going to say this h is equal to 0, and I'm going to lift this. Mass up, and I'm just going to assume that it's going to go up 1 meter, right? Well, how much energy does it take to take this, which has got a mass of 0.5 kilograms? How much does it take to lift it up 1 meter? Okay, so we're going to have 0.5 times 9.8 is 4.9 times 1. So I'm going to take my change, or my potential energy final minus my potential energy initial, change in potential energy. Well, since I'm close to the surface of the Earth, I can just use mg delta h. Okay, so I'm here at 1 and I went down to 0. So that's 4.9 joules. What if I made the ground? What if I made the ground equal 0, right? Now, presumably that is 1 meter. That's 1 meter above this. So my initial position is at 1 and my final position is at 2, okay? Well, now what I'm going to say is my final potential energy is 9.8, which is 0.5 times 9.8 times 2. And now I'm going to go and subtract my initial position, and that is going to be 4.9. So I'm going to take 9.8 minus 4.9, and that is going to give me 4.9. 4.9 joules, the same as when we had h equals 0 right here. Well, what if I made the ceiling? What if I made the ceiling 0, right? And my final position right here would be at -2, And my initial position was at -3, okay? So now I could say mgh, so that would be 0.5 times 9.8 times -3, okay, which would be -14.7. And my final would be 0.5 times 9.8 times -2, which would be -9.8. And now I'm going to say final -9.8 minus initial is -14.7. And the difference, 4.9, positive, right? So H equals 0. It doesn't matter where the H equals 0 is, okay? As long as we have it established. But, okay, when we start talking about the universe, right? Let's kind of go to get our sort of picture of the Earth here, okay? Now, when it comes to the Earth, right, where do we make H equals 0, okay? Do we make it on the surface of the Earth? Well, what if we're talking about the moon? What if we have the moon up here? Is our H equals 0 going to be at the surface of the Earth? Okay, that's going to be really, really weird. What if we're talking about the sun? Is the surface of the sun going to be H equals 0? What about Alpha Centauri? What about the center of the Milky Way or the Andromeda Galaxy? So the problem when you're dealing with huge parts of the universe is agreeing of where H equals 0 is, okay? So here's the riddle. Where is a position where everything in the universe is the same distance? Everything in the universe has the same distance from this particular point, okay? It seems like it is an impossible task, okay? But the answer is that infinity is where H equals 0. So at infinity, H equals 0 is at that location. Now, if we go back to our equation here, all right, now, if we look at here, so here is our change in potential energy, which would be U final minus U initial. It'd be equal to G M1 M2 over 1 over R final minus 1 over infinity, okay? Because our initial position is infinity. Well, 1 over infinity, obviously, okay, is equal to 0, okay? So now, if we, as oftentimes when, for example, when we start a stopwatch, right, we normally just assume that we start at 0. So when we say delta t and it's 10 seconds, we just say 10. We don't say 10 minus 0 because we just assume that that's where we started. Essentially, the same thing is happening here. So if we want to know what our potential energy is, and I forgot to take this negative and put it out here, okay? So we're going to have negative G M1 M2 times 1 over R. 1 over R. Now we can put that, I suppose, we can put that right there, okay? So this is how we calculate. This is how we calculate our potential energy, and this is gravitational potential energy is equal to negative G M1 M2 over R, which seems weird, okay? So now we can kind of think of this relative to anywhere, and just like in my example, here, we could calculate what is the change in gravitational potential energy between here and here, okay? So we could use, the same thing, and we could use the radius of the Earth, and then we could get the radius of the Earth plus 1 meter, okay? If we use the radius of the Earth and the radius of the Earth plus 1 meter, okay, then we would get 4.9 joules. Okay, so it's the same thing. So near the surface of the Earth, we can use 9.8. All right, you guys, we're going to use this equation right here, and we're going to calculate we're going to calculate something that is very similar. That is very similar to your question of the day. And that is how much change in potential energy if you have a 5,000 kilogram satellite and you move it from the surface of the Earth to a position where it is in geosynchronous orbit. Now, the geosynchronous orbit, remember, was the answer, or at least the preliminary answer, was 4.23 times 10 to the 7th meters away from the center of the Earth. Okay, and that be the first answer you got using Kepler's third law. You could also look, as I think I mentioned in my lecture yesterday, and the question of the day yesterday was, if you looked on page, for example, on page 371, they do that radius of a geosynchronous orbit using a different method than Kepler's third law, but they still going to get the same answer of 4.23 times 10 to the 7th. All right, so now you guys, we're going to do a quick sort of easy problem here, and we are going to calculate how much energy it would take, for example, one kilogram, if we were to move it from the surface of the Earth to a point of 100 kilometers above the surface of the Earth. Okay, so let's do that. Okay, now the difference, you guys, the difference between the surface of the Earth and 100,000 or 100 kilometers. Okay, it's a difference of 100,000 meters, right? So 100,000 meters still seems kind of fairly close to the surface of the Earth. So let's first do an MGH, okay? So if we do an MGH, that's going to be 1 times 9.8, okay, times 100,000 meters, okay? Now remember, that's the change from the surface to that new altitude. And obviously, I picked these numbers to make it really easy. So the answer would be 980,000 joules. Okay. Now, you guys, we're going to use this equation of the potential energy, or the change in potential energy, is going to equal to big G. We're going to have the mass of the Earth times the mass we're moving, which is going to be 1. And we're going to take the difference between R final minus 1 over R initial, okay? And this is, we'll put this change in potential energy, we're going to have a negative there, right? So we're going to have 6.67 times 10 to the negative 11th, okay? Now, you guys, the mass of the Earth is 5.98 times 10 to the 24th. You could find that in your reference material. Even if you made that 6 times 10 to the 24th, you're in the right ballpark. And then we're going to multiply that by 1, just a mass of 1. And now we're going to say 1 over R final. Now, the radius of the Earth is 6.37 times 10 to the 6th meters. Okay, and this is going to be our initial position. So let's put that in first. So 1 over 6.37 times 10 to the 6th. Okay, now if we take 6.37 and we add 100,000 to that, okay, now that's 1, you guys, that's 1 times 10 to the 5th, which means that when we add it, that's going to be in this position. So that's going to be 6.47 times 10 to the 6th. Okay? So now we can see, at least looking at these two numbers, right, they don't look like they're hugely different. They do not look like they're hugely different, but they are different, right? So we should end up with something that's less than 980,000, because that's if the G stayed constant. And we know that the G is getting less and less, but even at 100,000, or even at 100,000 meters or 100 kilometers, the difference is not huge, but it's still significant. All right, so you guys, if we plug these numbers into our calculator, and I'm looking for a calculator. Okay, so I'm first going to do this. So I'm going to say 6.47 times 10 to the 6th inverse minus 6.37 times 10 to the 6th inverse equals. Now we are at negative 2.4 times 10 to the negative 9th. Okay, so I'm going to plug that in. So this is negative 2.426 times 10 to the negative 9th. Okay, so I'm going to multiply that by 1, multiply that by 5.98 times 10 to the 24th, and multiply that by 6.67 times 10 to the negative 11th. And remember, I forgot to put in this. That's going to be negative, okay? So now I put in negative, and I end up with this equaling 968,000 joules, okay? So this is the change in potential energy. The change in potential energy between the surface of the Earth and a location where the geosynchronous orbit would be. That's going to be the question of the day. We're only going 100 kilometers higher. So you're going to kind of use the same method here, except your final is going to be the surface of the Earth, and your initial is going to be your location for a geosynchronous orbit. Okay, clue here, that's going to be 4.23 times 10 to the 7th, 4.23 times 10 to the 7th, which is the radius of a geosynchronous orbit with the center of the Earth. So surface of the Earth to the geosynchronous orbit, 4.23 times 10 to the 7th, okay? Now, you guys were only talking about the change in potential energy. So in tomorrow's lecture, we're going to talk about the kinetic energy of those, because if you were actually starting off at Cape Canaveral, okay, and this is going to be tomorrow's question of the day, what would the energy be? What would the minimum energy be to move it from Cape Canaveral up to the International Space Station? And what we have to do there is take into account kinetic energy, and that's to put it in orbit, not just get it there. All right, ladies and gentlemen, until then, we will talk to you soon.